Hello, everyone, and welcome to the March installment of the NWA webinar. My name is Becca Mazer, and I will be your host for today's webinar. Some of you may still have snow, like I do up here in Alaska. Some of you might have some severe thunderstorms that you're dealing with, and some may be drying out and primed for fire season. So it's a great time to talk fire weather. But first, let's talk about a few logistics before we get started. So we want to welcome you to the webinar, but everybody here will be kept on mute for the entirety of the talk. We certainly encourage you to ask questions or send along comments to our speaker, but please do this using the questions GUI or the chat GUI in GoToWebinar, or on Twitter using the hashtag NWAWebinar. I will then read the questions and comments at the end of the presentation. You can also follow along on Twitter using the same hashtag or the @NWAS account. And lastly, this webinar is being recorded for later viewing. So I am pleased to introduce our speaker for this month, Greg Murdoch. He is a lead forecaster at the NWS Midland, Texas office, and he's an incident meteorologist, or IMET, and is heavily involved in radar applications to the fire, weather, and alerting process. So, Greg, the floor is yours.
Okay, can you hear me all right now? All right, very
yes,
good.
I can.
Appreciate. Okay, very good. I appreciate the opportunity to speak today and share some of the work that we've done, published back in, I think, in early 2019, using the radar, 88D radar to observe some fire mode characteristics of wildland debris plumes, and even look at some tactical applications of what we might be able to determine from the mode. Everybody's pretty familiar with using the 88D to, see and notify people on fires about atmospheric features like cold fronts or low-level jets or convective rolls, things of that nature that will result in nonlinear fire movement or behavior. But this work kind of takes it to a little bit of another level, and we can kind of think of it as a basic principles approach to analyzing debris plumes as detected by the 88D, and hopefully too it'll make you consider and think more about fire as being an atmospheric phenomenon. And one of the things that we really wanted to do was look at some of the research that was out there and apply those conceptual models to be able to look at these different modes of dry convection, as we're calling fires, dry convection as opposed to thunderstorms, moist convection. And we kind of looked at the common fire mode nomenclature that everybody's probably familiar with, the plume or the wind driven, but there's really a little bit more to it when you start looking at these plumes closely and in the environment that they're in, the wind and the wind shear, the time of year, things like that. And so what we did was we went through this research that Kiefer had put out, a couple of different papers where he highlighted through these simulations these different modes of dry convection, and we wanted to see if we could kind of confirm his simulations in the real world. And so we looked at some cases, a couple of fires that I was on as an IMET, and then we wanted to try to see if there's any sort of really kind of application to what might be going on in the ground and with respect to some kind of tactical information that we could use. And so first off, when we observe a debris plume on radar, where a lot of people say, well, look, there's a fire on radar. Well, of course, the radar is not really detecting fire. It's really looking and observing the debris plume. And as a reminder, the 88D radars are not sensitive enough to be able to detect smoke particles. So what they're they're really seeing are the lofted scattering from pyrometers. So different kinds of embers, they may be burning or non-burning, but that's what the radar is really detecting, the 88D radar that is. Now those smaller radars like the LiDAR, those do detect smoke, and you can see even more so the circulation and the things going on within the updraft and the debris plume with the LiDAR. But of course, in the operational setting, the National Weather Service meteorologists, of course, are using the 88D. And so the key concept here about the debris plume is that the formation of the debris plume is a result of an increase in of combustion that accelerates and lofts particles into the atmosphere. And the good thing for us being meteorologists is that just like in moist convection, there's this idea of atmospheric continuity. The same thing with this dry convection is that the continuity equation, is still there. And so, I've heard it simply put as in, up, and out to describe that continuity process. And so we kind of keep that in mind, even when you look at convection, whether it's moist or dry, one of the things you should be reminded of as a meteorologist is the continuity equation. And so what Kiefer did was he varied the ambient wind and the buoyancy, and found that as a result there were different modes of convective characteristics that he saw, and he basically broke it down into the multi-cell and the intense convective plume. And pretty easy to kind of understand and kind of conceptualize the multi-cell, in the strong advective environment, with that stronger wind, there's less residence time for the air to remain over the heat source, and so it gets heated and then it gets moved away, and it just kind of have this continuing process. And for the difference with the intense convective plume is that it's in a weak environment, and so the residence time over the heat source is a lot longer, and so you get a different structure of the updraft, and as a result the debris plume, which is more or less a proxy for the updraft. So that residence time is key. One way to visualize the idea of these debris plumes was buoyancy, and that idea of buoyancy kind of was a recurring theme over and over in these papers that we were looking at as we kind of did our research. And that, again, should be a familiar concept with meteorologists. Obviously, it's used in the realm of moist convection, but it does help you conceptualize what is going on in dry convection as well. And so a researcher, Fail, in 2007 illustrated this idea of thermal bubbles, which basically this illustration here indicates the air over the fire is heated, is lifted, it kind of bulges out and gets, of course, higher and higher as it's heated more and more, and then the wind finally kind of pushes it away from the heat source in the form of a bubble, a thermal bubble, or a parcel, if you will. And then that process is just repeated over and over until you lose the heat source. And what Kiefer saw in his simulations, these three charts are from his simulation. The one on the left there, the weak multi-cell mode, was the one that has the shallower, weaker velocity couplets, and you can actually kind of see a bit of a sign or a bit of a wave pattern And let's see if my pencil's going to work here. No, it doesn't seem. Let me change colors here. Maybe the red will work. Well, no, it's not working. But anyway, when you look at the wind vectors there, you can kind of see a wave, kind of a wave in the couplets, kind of showing you where the updraft and downdrafts are embedded within the cells, and the cells are represented by the shadings there, the darker shading showing the updraft, and the dash showing the downdraft. And you'll notice too that on the weak multi-cell that the cells don't extend very deep in the atmosphere. You can see the scale in kilometers there on the left, that they're only going up to around 2.5 or so at a maximum on the vertical scale. As you look to the strong multi-cell case, you'll see that the wind vectors are shorter, and so the advective environment is going to be weaker, and as such, the cells are deeper, more organized. The up and down velocity couplets are much better visualized and organized. And then the screen on the right shows us how we can track these individual thermal bubbles or cells as they move downwind from the original heat source. And that's kind of what the dashed line shows there, with a time progression starting at the top going down to the bottom, how we can follow along in time and space one of these thermal bubbles as it moves downwind. And so we take that idea and then we applied that to our first case study here, first weak multi-cell case of a fire in Northwest Oklahoma back in the spring of 2016. And we could see how these individual cells or thermal bubbles are identifiable. They're mostly discrete, but not totally. They kind of become more elongated due to the strong wind, and the deep mixing aloft kind of changes the shape of them from the original heat source. And then also too, as you look out in time, you can continue to follow them downwind. And in these cases, the debris plume maximum height will be further downstream than the maximum reflectivity back at the source of the heat at the head of the fire, showing that there's this general tilting and elongation of the plume due to the environmental wind pushing it along. And so in these cases, the tactical implications may include something along the line of a fast-moving fire. Of course, this was in a grass brush fuel environment, and so fast-moving, kind of steady state environment. Now, there certainly could be some erratic behavior, of course, with spotting downstream, as Kiefer pointed out. But in general, in this situation, we would be thinking of a fast-moving kind of steady state. And then the next case study that we have was in Southwest Oklahoma back in 2017. And this is the strong multi-cell case. And with this one, the thermal bubbles are easier to identify. You can see here the series of thermal bubbles that move downwind. They're not as distorted. There's pretty good continuity both in time and space. The frequency between cells is pretty consistent, kind of owing to the wind. The environmental wind hasn't changed and is consistent. And we can kind of see that the cell train may be a little bit longer and have more cells, more thermal bubbles than what the weak multi-cell case does. And you can again follow in time and space these as they move as they move downwind, kind of what we've shown here. And again, the tactical implication here indicates that there may be some steady state fire growth because of the characteristics of the consistent thermal bubbles. If you started to see the thermal bubble cell characteristics start to change, maybe the frequency with which they were being developed and formed changed, that might give you some indication that the rate of spread would be changing in the fire, and that erratic fire growth certainly is possible in this case. Again, Kiefer noting that due to mixing, you may be able to mix down some wind, maybe some higher wind that could affect the rate of spread, and also again maybe some drier air aloft might be mixed down that could also change the fire behavior a bit. And so staying on the idea of the multi-cell case here, the next thing we wanted to look at was the maximum top with respect to the low-level reflectivity maximum. And what he observed in his simulations was what we were also able to observe in real life. Not only that we're able to track them downwind, but you can see in the top screen there on the radar showing the high reflectivity just north of Buffalo, Oklahoma, and that's in the DBZ representation. The image down below is the height of the debris plume, and you'll notice that those two correlate to a very low height. But as you go downwind there on the max height, you start to see the reflectivity or the reflectivity drop out. It weakens, but the max top goes up, and so you see this tilting again of the debris plume that increases with height as you go downwind. And again, that's what Kiefer's simulation showed there in the black and white photo, showed that the max top is downwind from the low-level maximum reflectivity. And so now moving on to the intense convective plume characteristics. This one's probably maybe a little more popular. This is the type of fire of debris plume that's observed in the western United States, typically during the summer fire season, when the weaker winds aloft favor a more vertical or erect plume or updraft, as compared to the more laterally displaced ones that we just observed that are frequent on the Great Plains. Now out west, you can also get, you have days out west in the summer fire season, that you get a strong advective, environment in the updraft area, and that plume won't necessarily be upright and vertical. It'll have some tilt to it as well, but in general, wind in the western areas isn't as big of a factor. And so what we saw in the simulations from Kiefer was that the updraft, tends to be upright, pretty vertical. It's pretty continuous. It's a lot deeper typically than what we see with the multi-cell setup, and the velocities also tend to be stronger than what we saw in the multi-cell case. And that makes sense because the western fires are burning in heavy timber, so your heat source tends to be just hotter, simply just hotter. And then also too, you can see in the simulations here, it's kind of neat that at the top there, on either side of the red oval, you can see the divergence at the top, and down at the bottom there, you can see the convergence in the low levels, again, supporting this idea that there's this continuity in the atmosphere associated with fires in these dry convective environments, just as what one would expect to see in a moist convective environment, trying to diagnose environment for a thunderstorm to form in. And so again, we want to use the idea of buoyancy to help us visualize these intense plumes, the vertical nature of them. And back in 2008, a couple of researchers put out a wildland fire vortices paper that is an excellent paper that I highly recommend meteorologists, especially meteorologists interested in fire, read. It's very thorough, but he introduced a couple of concepts in there that were pretty important, and that included using the idea of buoyancy-induced shear to describe the updraft, and was able to kind of put that in context by describing this idea of what's called transverse vortices, and to visually being able to observe those as those kind of on the back edge of the updraft, as if you were kind of standing back, looking up at it, you just kind of see these boiling appearance of the debris and the smoke moving up, and that's the transverse vortices. There's a kind of a whole bunch of them that they end up kind of collecting or amalgamating as they move up the updraft and get higher and higher. And he went on to has this schematic that really is pretty eye-opening too. It helps you formulate a conceptual model of what might be going on. And so you can see the wind shear, an increasing wind shear profile with height. You see the fire area, right in here. Hopefully you can see my little red dot here indicating the fire area, and how the general wind is just kind of tilting over the updraft slightly. And just like is considered in thunderstorm environments, how you have this ambient source of horizontal vorticity, you have the same thing going on in a fire environment. And so the fire basically, one way or another, ingest this ambient source of horizontal vorticity and lifts it. And that lift, of course, that's the buoyancy that we need to be thinking about. And then you can see, right in here, for example, this would be spinning, and that as this climbs, so in time, so they're saying that's time one, there's time two. It's getting higher and higher in the updraft, and as that is lifted, it is also spinning horizontally, and that whole kind of process there is what he describes as the climbing transverse vortices. And that's really pretty cool, because we'll actually be able to identify that in radar data here shortly. And so here's our real life case. This was a fire in the Southern Sierras that I was on as an IMET back in 2016. And what we have here on the right is the volumetric generated using GR2, showing the debris plume, and the images on the bottom on the lower left are the reflectivity and the maximum top. And so what we look at first here in the time series, the first one, we more or less see a continuous updraft over the reflectivity max. So right above my time here, here's the reflectivity maximum on the lowest elevation. So the updraft has a little bit of a tilt to it, but it's a weak environment, advective environment, and so it's more or less continuous, and it's deep. You can see here on the scale, it's going up to over 30,000 feet up through the mixed layer. I don't have it shown here, but in the paper that we authored, we do have some soundings on it that show the mixed layer for this, and the mixed layer was basically right in through here, around 20,000 feet or thereabouts. And so we basically have an overshooting top of the convective part of the updraft. So deeply mixed. And then you can see it slowly, the debris plume slowly advects and sinks as it cools, and the debris, you know, slowly falls out as you go in time. And down at the bottom here, we want to show, this is the farthest left here is the maximum reflectivity at half a degree with the maximum height of the top of the debris plume. And the little yellow cross here is the same point. So the surface maximum reflectivity is at the same general spot as the maximum top of the debris plume. Again, showing us that it's vertically stacked, and again confirming the conceptual model that Kiefer had in his simulations. Now then, going back to some other things that we were able to learn from our radar analysis, you know, we were just talking about the transverse vortices and how they climb up the backside of the updraft, and that if you were in the right spot, you would be able to see them. And see these two little protuberances here on the backside? That is the transverse vortices climbing up the backside of the debris plume. And then as we go down in time, of course, the updraft, the debris plume, the column becomes more organized, and we start to see this really neat organized feature that we call the back sheared convective plume. And it's kind of the you know, the culmination of the updraft. It tells us that it's fully developed, and what's pretty cool is that it is analogous to the back sheared anvil that you might observe in a severe convective storm. And that again is another indication to us that there's this atmospheric continuity going on with this dry convection, and that there's really some organization to these structures of these debris plumes that can be ascertained when you look closely at the radar data. And you know, one thing that going back to the paper, the Vorticity Wildland paper, the observance of these climbing transverse vortices weren't really, they said they weren't really associated with a change in fire behavior, or excuse me, they were with a change in fire behavior, largely a change in rate of combustion. And so it's key to be looking for those features in your analysis of radar. It's just like when you're analyzing radar in severe thunderstorms, you know, you're looking for key features, whether it's some kind of velocity feature or BWIR or whatever. You know, use that same kind of idea when you're looking at debris plumes on radar. You may be able to you know, add some real value that could be applied to your operations and to those out in the field. And the second case we have, this was a Texas fire in 2015 of the intense convective mode, and we see the same thing. The low-level reflectivity is basically pretty well correlated to the updraft, just a little bit of tilting there, but not too much. It's fairly deep, not near as deep as the previous example, as this was in a little bit of a cooler season. This was more into the early part of fall in central Texas, and the mixing wasn't as high, and the plume again is kind of, you know, drifts downwind and settles. You can see how it kind of settles back down into some lower altitudes as it cools and the debris kind of starts to fall out. But we see the same characteristic down here in the left bottom, where the low-level reflectivity maximum is correlated with the maximum top of the debris plume. And we also, again, we can see hints of the transverse vortice right here in the first frame, in the first frame of its development. And later on, you go down just 20 minutes later, you can start to see a pretty good indication of the development of the back sheared convective plume as the thing kind of, chugs along. And again, that tells us that there's this continuity of the atmosphere with the fire. And so we got that, so you have some low-level convergence. And what for plume fires, the problem with that is that so you have convergence coming in from many different directions, feeding into the updraft. And that results in the potential for increased erratic movement. As mentioned earlier, the general environment in the western U.S. for fires is a weak advective environment. So the fire is not necessarily being pushed along by the ambient wind. It's really kind of being more dictated by the fuel, where the best fuel source is, and these other more difficult to measure things like low-level convergence and how that impacts the erratic movement. And then I wanted to quickly show this. There's a lot of interesting things going on with radar analysis nowadays. With the last couple of years, there have been some really big fires out in California and Nevada that have resulted in some Firenatos, and so people are starting to look at and study that. And one of those is Dr. Neil LaRue out at the University of Nevada, and he's collecting his cases, to build some some research and some conceptual models. And this is from I'm trying to remember which fire this is. I think this is maybe the Cherry Creek fire in California, either late last summer or real early fall. And what it shows, so just to orient yourself here, the radar is towards the left of the screen, but the fire is up towards the upper right of the screen. And so using these conceptual models, he's able to formulate this idea of circulations and rotations within the debris plume. And this is with 88D radar, which is encouraging. That will, in some cases anyway, depending on the fire's proximity to the radar, we're always going to be limited by that, unfortunately, versus these mobile radars that can just go right up to it and sample, have a really good sample. But in this case, the radar was able to sample it pretty well, and it showed this circulation that formed about the same time as a deep pyro CB developed on top of this debris plume, on top of this updraft. And LaRue seeing a strong correlation between when that develops a pyro CB, or maybe even a really well developed pyro Q or TCU atop of the updraft, that you start to get this reverse flow signature. That's what you're seeing here in the red, this reverse flow signature developing. And kind of going back to the conceptual model here in the upper right, you can see this flow right in here, downwind in the low levels, is kind of that reverse flow kind of feeding in. And then on the periphery, on the flanks here, is where you're going to see your circulation spin up, where your vorticity maximums are going to be. And he's really using this this bifurcated conceptual model of a fire and a fire updraft to apply these these results to be able to pick out the circulation. And here on the right flank, you can really see this anti-cyclonic circulation develop, and there's all kinds of vortices. There's the entire column could be rotating, kind of like what a mesocyclone might do. But then further downwind, there's this idea of vortex shedding, and this is probably a case of that, where there's this vortex shedding due to some instabilities and shear downwind. And anyway, he's collecting all these cases, and he's basically going to have sometime I expect he's going to have a really interesting paper and results that come out as a result of this. And that's kind of where all of this, is really kind of heading. And so just to kind of summarize, some of these inferred tactical applications, really what I really want, meteorologists to start thinking about is using some of the conceptual models and things that about moist convection, applying them to dry convection. There's each one kind of has a counterpart, rate of spread and rotation. Is it a steady state movement, or are you getting some kind of erratic movement of the fire, similar to what you might in a supercell? You get deviant motion in supercells. You get a right mover or a left mover, or it speeds up or slows down because of something in the ambient environment. You get these different rates of combustion, analogous to storm intensification and new updrafts. And so there's this opportunity to think about dry convection with some of the knowledge that you already have from moist convection, to help kind of formulate some ideas and concepts for you. And so at the end of our paper, we kind of came up with this table to summarize the different fire modes and some of the radar signatures, along with the atmospheric environment, and then of course some of the impacts or tactical applications. And this was just kind of a cursory table, but if you start to see some of these things in your analysis of debris plumes, maybe we can add to this and have a more comprehensive list of signatures and the environment and impacts and things like that. Now it's always going to be difficult to come out with some direct application from radar to exactly what's going on the ground with a fire, because a fire is so non-linear. It changes so much because of different, it could be firefighting tactics that change it. It could be the topography. It could be the fuel. It could be the weather. And so it's changing quite frequently. And so it's a lot of times difficult to make direct tactical applications from radar, but you can do some things. And I think the more that we all start to look at it and get interested in it, that will get better. And again, as I said earlier, if we viewed this dry convection similar to the way that we do moist convection, that would be good, because you already have a lot of conceptual models and understanding of how moist convection works and how shear impacts environments or updrafts, and how buoyancy also results in different characteristics of storms. And so use those ideas in debris plume analysis. And in the long term of the Weather Service operations, there may come a time where there's this future shift in the way things are done, this paradigm shift, and that's going to include things like using this high resolution satellite data. We have 1 minute data that comes out now when we get these mesosectors going, and they're mesosectors are being implemented on these big fire days, big fire weather days. So the data sources out there really becoming favorable to use to help analyze debris plumes, and how we might be able to relay that in terms of tactical information to our partners. And so that's all I have. Thank you for the opportunity today, and I'll be happy to answer any questions that it might come about.
There we go. I think I'm unmuted now.
Okay,
thank you so much, Greg, for that awesome talk. So much great information, and pretty new, in terms of applying radar imagery to take a look at fires and what the radar could tell you about a fire, as you said, of course, obviously, depending on all the different characteristics of the environment surrounding the fire. So thank you so much for that talk. We have a couple questions. You may have touched upon this a little bit in your discussion, but could you maybe talk a little bit about how do you incorporate, say, the elevation of the radar beam as you go out distance, and how that could influence your interpretation of the cell types in the plume?
Well, that is a challenge for sure, since the radars are obviously fixed. To be able to sample, at the most effective distance and height from the radar, it's just going to have to more or less be by fortunate circumstances. So it's just like when you look at thunderstorms, when you look at them from a long ways away, you lose some of the detail, and that's going to be the same case when you try to analyze a fire that's maybe too far away. You may only actually be seeing the mid portions or the top of the fire, and you won't be able to tell too much about it, other than maybe some general trends. If you're able to sample the top of it, then you're kind of able to get an indication of the change in the maximum top, and therefore you can infer that just simply some changes, increasing and decreasing changes. So that's always going to be a challenge that we face, and not too much that we can really do about that, unfortunately. But what you really want to be doing also is using other data sets, overlaying or side by side with some of the high resolution satellite data, to give you an idea. Has a pyro Q formed? Has the pyro CB formed? And even if you're sampling the top of the storm or top of the debris plume from a radar that's a distance away, you might be able to use some of the dual pole data to show you the transition. You might be able to use the CC correlation coefficient to see the difference between the plume, which is going to have a low correlation coefficient, versus the high correlation coefficient in precip. If it does go to CB, you might be able to pick up some of those hydrometers, and so you still may be able to do some things, but that is always going to be a bit of a challenge.
Understood. Yes. And in that discussion, it seems like you answered the other question about, looking at the multiple radar tilts. Could they give you a better depiction of intense versus weak plumes? Do you have anything further to add to that, or have you? Do you feel satisfied with that answer already?
I'm sorry, I missed the first part of your question. What was the first part?
Okay. Sorry. The question was, looking at multiple radar tilts, does it give you a better depiction of the intense versus weak plumes or other characteristics? You sort of answered that already, but I was just wondering if you had anything further to add.
Yeah, looking, if you're fortunate enough to be in a place where a couple of radars are sampling a debris plume, you might be able to gain some additive information. Again, it's just like severe weather, moist convection. Here in Midland, a lot of times, we'll want to use the radar at San Angelo to interrogate a storm that's, close into Midland. We might get a better idea of what the updraft is like. And so it's going to be the same thing with debris plumes, that, you might be able to, jump to another radar and get a better sample of the upper part of the fire, for example, than down low. And so, you can get some additive information and help you determine what it's going to be like. And then, of course, you still really want to rely on, what's the ambient environmental condition like with respect to wind speed, vertically. How is it changing vertically? That's going to tell you largely, what type of fire mode you're going to be dealing with.
Excellent. And let's see. So I guess just for my curiosity's sake, you did mention bringing, like, say, a mobile radar closer to a fire for observation and analysis. How often does that occur?
Not real often. The San Diego State University, in the past, I'm not sure if they have it today or not, I think they do, but they have a research radar that they can take out into the field in certain situations and set up right next to a debris plume, just maybe a few miles away from it, and sample it really well. And so some of the research, and I don't have, so my recommendation too, I wanted to mention, was that go to my references on the paper, and there's some really good papers in there that you want to read. One by McCarthy, that Forthofer vorticity paper. There's some papers in there by Lindley. And then, of course, there's several papers in there by Dr. LaRue that I mentioned earlier that are really, really good papers. And they go into much more detail about using that mobile radar. They use that radar to base a lot of their findings on. And so those are really good sources for that kind of radar analysis.
Excellent. Well, it looks like we don't have any more questions, so I guess we'll wrap it up. Once again, thank you so much, Greg, for being a part of the NWA webinar series. We really appreciate it. And I hope you and the audience out there learned, something new about analyzing potential fire conditions off of looking at the radar imagery and the fire plume, and use that potentially in your operations as you're chatting with your IMETs or other fire partners out in the field. So that is all we have for now, everybody. So stay tuned to the newsletter and the NWA social media accounts for information on the next webinar. Thanks again. We'll see you next time. And as always, be safe and stay healthy. Thank you.
Okay, thank you, Becca.